Good morning. My name is Niki Georgiou, and I will present my research which focuses on the kinematic analysis of rigid bar-linkage system typologies. My presentation consists of a brief introduction, a presentation of the effective translator approach, the kinematic and structural analysis of the case study conducted. Adaptive architecture defines a design that responds dynamically to changes of the environment and pattern of uses. Main characteristics of deployable structures are self-weight minimization, easy storage, transportation, and reuse. Deployable systems can also be self-erectable and reconfigurable. Such systems comprise tensegrity, scissor-like element systems, and bar-linkage structures, which are of a great interest in the field of architecture and engineering. The first typology of such systems refers to tensegrity structures, which comprise interconnected spatial, reticulated, and lightweight units that are composed of compression members and cables, as shown in Figure 1. The second typology refers to planar scissor-like elements, which consist of two bars connected to each other with a rotational joint. The application of the systems principally follows a two-stage form from the closed to the open deployed one, as shown in Figure 2. Linkage systems refer to a category of deployable and reconfigurable modular structures with high flexibility and controllability, whereas pin joints connect a series of overlapping rigid segments. Linkage systems consist of single members or may be further developed to hybrid elements. The reconfiguration of linkage systems may be achieved through a rotational or linear motion actuator position on one of the fixed supports. The effective crank-slider approach is the basic structural and kinematics element of a planar linkage system that is consisted of n serially connected rigid links with pivot joint between them as shown in Figure 3. The two ends of the structure are supported on the ground through a pivot joint on one end and a linear sliding block on the other end. The configuration concept is based on stepwise adjustments of the joints, where in each step the break of one intermediate joint is selectively released, while the pin joints at the supports are always kept unlocked. In this way, every angle of the N-bar linkage system is transmitted and adjusted to its target position step by step, converting the mechanisms into a generic one degree of freedom system and in particular in an effective crank-slider system. In view of the above, the proposed structure refers to a configuration concept of spatial bar linkage structure that is based on the effective crank-slider approach. Three basic linkage structures of 8, 12, and 16 rigid aluminium bars with lengths of 1.5, 1, and 0.75 meters respectively, and a sliding block have been investigated in three possible typologies. A bar linkage or simple system, a bar linkage with secondary system of struts and parallel continuous cables to the links or hybrid system, and diagonal ones or cross-hybrid system. The approach has been examined from an initial, almost flat configuration of the linkages to a specific target arc-like one with span of 6 meters, which amounts to the half of the structure's initial length in its non-deployed, almost flat position. The stepwise reconfigurations of the three linkages with different number of bars are presented in Figure 4, 5, and 6. The simulation study refers to the preliminary kinematics and the finite element analysis of the linkage systems in their respective three different typologies. Each linkage has a configuration that involves an initial form and a target configuration. The configurations are defined by the following position vectors, which demonstrate the individual joint angle between the bars. The deployment steps of the simple planar linkages with 12 bars from their initial to the target position are shown in Figure 7. while the deployment process of the hybrid and cross-hybrid linkage systems with 12 bars is presented in Figure 8 and in Figure 9. The only cases taken into account are the self-weight of the system and the pretension of the cables in the hybrid systems. The structural analysis results for all system typologies are presented in Table 1. A comparison among all systems reveals that the cross-hybrid systems with higher number of bars, 16 bars, has the highest self-weight as well as bending moment in the beams and deformation. The 8-bar hybrid system has the highest maximum relative cable length variation. The linkage systems with lower number of bars have the highest maximum sliding block displacement. The comparative analysis results for all systems are presented in Figure 9. Highlighted in red, you can see the cases that have the maximum forces. The cross-hybrid systems register higher maximum bending moments in the beams due to their comparatively increased self-weight and bending moment portions induced by the pretension of the diagonal cables. Finite element analysis of the maximum bending moments in the members induced by the pretension of the cables as the only load acting on the system has verified this influence. The hybrid system register comparatively higher maximum relative cable length variations. The current paper presents a deployment approach for bar linkage structures in 3 different typologies based on the effective translator method. The study demonstrates in a first step that effective designs may promote desirable features like low energy consumption during motion, modular assembly, self-erectability, and reconfigurability. Thank you for your attention.